Professor Nirmala Ghosh on very interesting problems on optics and photonics, and which led to a number of very good publications in international journals. And after that, he went to the University of Calgary to do his PhD. And there he got many scholarships and fellowships, in particular the Dean's International Doctoral Recruitment Scholarship, the Alberta Innovates Graduate Student Scholarship, the Isaac Walton Killam Doctoral Scholarship, and the ICE High International Doctoral Scholarship. And he did his PhD with Professor Christoph Simon, one of the leaders in the field of quantum information. And I don't want to say anything about his PhD work because that's the subject of his talk. So with these few words, let me now request Sumit to give his talk.
Thank you, Professor Das, for the great introduction. This is the first time I was introduced, I guess, giving a big talk. But thank you so much. I will start with my talk. I'll share my slides first. I think you can see it now. The slides?
Yes.
Okay. I did my PhD from University of Calgary under Professor Christoph Simon, and this is the work that I'm presenting today is my PhD thesis work. So the title of the thesis is the same, the Photonic Quantum Technologies, Non-Destructive Photon Detection and Quantum Simulation in Solid-State Systems. So the thesis is mainly focused on photonics quantum technologies, which is nowadays getting a lot of traction in both quantum networks and quantum computing. Photonics is essential in quantum networks in the sense that quantum networks, it is kind of sure that quantum networks would be made out of light, out of photons, in contrast to the quantum computing, where there is still many systems which are competing to be the primary system of interest. I mean, there is superconducting, there is ion traps, there is atoms, ultra-cold atoms, but in network, it's just it's kind of sure that it is photons. The quantum network will be made of light because the light has such high speeds. In optical fibers, it's not at C, it's like 2/3 of C, but still it's very high speed, and it interacts very less with the environment. So due to this great advantages, network will be made out of photons. But the issue with both this quantum network and quantum computing is that here the photons are the single photon level. And then the qubits that are made out of the photons using either the polarization of the photon or other states, whether it's spatial, temporal, other states of the qubit that are kind of fragile, and those create some problems. One of the problems in this photonic technologies is knowing the presence of the photons without destroying them. And that is the topic of my first project. I've done 2 projects in this related to photonic technology area, and I'm going to the first project right now. And that is quantum non-demolition measurement of photon number. Here we want to measure the photon number, but do not destroy the photon, or do not measure its qubit state. So suppose a photon comes in. Suppose a photon comes in from a source. Now you want to know whether the photon has arrived or not, or it is lost in the way, or something else happened, it was not emitted, or something like that. So you want to know whether the photon has arrived or not, but you don't want to detect it and destroy it, like detect it in the regular sense, like regular commercial photon detectors, and destroy it, or you measure it qubit state. You don't want to do that. You want to keep it so that you can use it for later, for other quantum information purposes. So such a QND measurement, this is the quantum non-evolution measurement, is called in short QND measurement. That's what I'm going to use all through the talk. So QND measurements have application in quantum networks and quantum computing. We were mainly motivated by the application in quantum networks because, for one thing, that's what we did in our group. We are a quantum network group. And also this is something that is really getting up these days, and hence this is one of the big motivations. So I will first describe a bit in brief what a quantum network is and how it will be made, things like that. So definition of a quantum network is that it will transfer qubits from one place to another. So qubits are quantum bits, which can be made out of many things, many different degrees of freedom of a photon, say polarization, or a spatial qubit, or orbital angular momentum qubit. But these photons, these qubits, they have to transfer from one place to another. And what will be the usefulness or application of such a quantum network that can transfer these qubits? We can perform quantum key distribution for secure communication using these qubits, using the quantum network, or we can create that. This is the long-term goal. The quantum key distribution is a short-term goal. The long-term goal is creating a future quantum internet that will give massive power to quantum computers by doing distributed quantum computing over the quantum internet, or it would be beneficial for something that we call quantum sensing, by which we can increase the precision of optical clocks or telescopes. So that is another research area that is emerging. Now the question is how to implement such a quantum network, how to build such a quantum network. And this does not have a straightforward answer, at least yet. Right now, the understanding is that there is like in different distance ranges, there are different solutions. So for less than a few hundred kilometers, like less than 500 kilometers, say direct transmission by optical fiber, like sending the photons through optical fiber is the best. Just like we send the optical pulses in optical fibers for classical internet. However, as we have to send single photons to the optical fibers, they tend to get lost. And after a few hundred kilometers, almost no signal reaches. And hence, for 500 to 2000 kilometers, it is not feasible. In that range, in distance greater than 500 kilometers, it's not feasible to just directly transmit the photon. So there, clever strategies were evolved using quantum memories. That's what we called quantum repeater. So these are fiber-based quantum repeaters. We're still using optical fibers as mode of transmission, but we are using memories and clever protocols called quantum repeaters, which I will describe next. However, again, these repeater protocols are not good for distances greater than 1,000 or 2,000 kilometers. It gets really complicated, and it does not hold anymore. I mean, the direct protocols does not hold. There are some protocols for longer distances, but for the first order protocols, the things that we are trying to make now, they don't hold for greater than 1,000 to 2,000 kilometers. And there, the best way is probably using low Earth orbit satellites. And this has been spectacularly successful over the last few years, and I will discuss that. But this is still limited to 1,000 to 5,000 kilometers because the low Earth orbit satellite, it will be between like 200 to 2,000 kilometers above Earth, and then it cannot see very far out because of the curvature of the Earth, and there are other issues. So, so this cannot go beyond 5,000 kilometers. Beyond 5,000 kilometers, one of the ways to go beyond 5,000 kilometers would be combining satellites and repeaters for truly global distances, to like 5,000 to 20,000 kilometers. Truly global distances, it will be combining the satellite links over the quantum repeaters. So this is what I'm going to describe, and this is where QND would be the most important in this, in the last one, in the fourth stage, where satellites and repeaters are combined to reach global distances. So first, let's describe what is a quantum repeater. Quantum repeater is distribution of quantum information by entanglement. Now, all of us probably know what entanglement means. It's where the quantum properties of two systems are correlated quantum mechanically. So if A and B are two photons, two photonic qubits, and the polarizations are given by H and V. So this, the polarization qubits are entangled like this, HH plus V over root 2. There can be other forms of entanglement like time bin qubits, which what we are using here. And time bin qubit is like the photon can be in this bin or that bin, and they are orthogonal. Like they can be either in this bin or that bin, and that is early. The photon can be this wave packet or in that wave packet, so early or late, or it can be in superposition of both of these. So the two photons like this can be in such a state, either both of them are in early or either both of them in late. So early plus late over root 2. That is like an entangled state. Now coming to the quantum repeater, the working of the quantum repeater, I have tried to explain it using 3 diagrams here. The first one is describing teleportation. So here, let me explain something first. The solid blue lines are 2 qubits that are already entangled. So this qubit 2 and qubit 3 are already entangled. However, the dashed blue lines like the C and D here, they are not entangled yet. So this is in C. I'm talking here about A, which are entangled, and here the A, I'm going to describe the basic teleportation, which all of you definitely know, but I'll still just go on and say that the 2 and 3 are entangled, 1 or 2 are in the same place, so we can make some operation on them, and one has an unknown qubit state, and what we want to do is that transfer the state of 1 to the state of 3, and we can do that by so we can do that by doing the teleportation operation on qubits 1 and 2, so the state of 1 gets transferred to 3, and that is teleportation. So we just do the operation on this. If these two are entangled, we can transfer the state of 1, qubit state of 1 to 3, and we have teleportation. And this is simply extended in the next figure, in figure B, and what we do here is that we have 2 simultaneously entangled pair of qubits, and if we do the teleportation operation here between 2 and 3, what happens? We are basically teleporting the state of 2 to 4. Just looking at the previous picture, here we send 1 to 3, and so it will be just similarly, it will be sending the state of 2 to 4. But 1 and 2 are entangled. So if we send the state of 2 to 4 by the teleportation operation, then what happens is 1 and 4 are now entangled. So we have increased the entanglement the distance. And this is called entanglement swapping. This was first proposed by Hans Friedel et al. In 1998. This is the backbone of the quantum repeater scheme. But the repeater scheme has something more in it. It has quantum memories. And this is what I'm describing next, the whole repeater scheme. So here there are like quantum memories, and these memories are separated from each other. So A and B are separated physically, but B and C are in the same place. And then C and D are again separated. Things like that. And then we are trying to establish entanglement between A and B. Now, how to establish that entanglement, how to know that entanglement is established, that's a whole different story that you have to go into details of repeater to know that. Suppose the entanglement, you try to establish entanglement, and the entanglement is established between A and B. Then it can be stored in the quantum memories, because A and B are in quantum memories, so it can be stored in there. But it may very well happen that it is established, the entanglement is established between A and B, but it is not established between C and D. So what you have to do is then you have to wait until the entanglement between C and D is established. and then you do the teleportation operation and extend the entanglement. And similar things for other links. You have to wait until your neighboring link is both the neighboring links are entangled, and then you extend that entanglement to have an entanglement over a longer range. And then once the bigger neighboring links are entangled, you can then again perform teleportation operation and extend that entanglement even further to between the two endpoints. So the main thing about this repeater is that you need quantum memories, because if you don't have quantum memories, in one shot you won't be able to entangle all the individual links. The probability of doing that is saying that the photons won't be lost in any of the links when you try to transfer photons to entangle the individual links. And that will be the same probability that you just do direct transmission from A to H and nothing gets lost. The probability of that is the same as saying that we would try to establish entanglement in all these links, A, B, C, D, E, F, G, H, and nothing, all of them will be simultaneously successful. That will never happen. If A to H entanglement, qubit distribution, that never happens, that directly sending qubits, that never gets successful. This will also never happen. That's why you need quantum memories and store the entanglements, so that then you can perform the teleportation operation when the two nearest links are both successful, and then you can extend entanglement. So this is my understanding of quantum repeater. This is the basic of quantum repeater. But this is about quantum repeater. Now the next part is about the satellites, which is the other strategy to transmit quantum information over long distance. And this approach has been quite spectacularly successful over the last decade. Chinese quantum satellite MISIAS with entanglement source was launched in August 2016, and since then it has been very successful. It has distributed entanglement over 1,200 kilometers in China. It has distributed the entangled pairs, and then it has done a lot of QKD experiments, and recently it has done entangled pair-based QKD experiments, like secure QKD experiments, entangled pair-based secure QKD experiments. Yeah, I think that was done in 2020. So this experiment has been very successful, and no one has established entanglement over such large distance, over thousands of kilometers. The previous was in hundreds by free space links from the Zeilinger group and other people, I guess. But so this is an order of magnitude improvement. It's a huge improvement. Repeaters are nowhere close here yet. Repeaters only work in tens of kilometers right now. And this is the satellite experiments which are worked over thousands of kilometers, but not to 5,000 to 10,000 kilometers, which will be like 10,000 kilometers will be like the distance between Delhi and London. No, Delhi and New York, I guess, something like that. And London and Delhi will probably be like 5,000 kilometers. But those global distances has not been achieved yet. To go to those global distances, we would need to combine both the satellite and the repeater approaches. And that's where quantum non-demolition measurement plays a key role. Is that if you want to do a repeater link over satellites, then you have to know that the entangled photons that are sent from the satellite that reaches the quantum memory. So they are not lost in their transmission through the atmosphere and because of diffraction. So what you need to do is you have to perform a quantum non-demolition measurement to know that the photons have reached the ground stations. So these are called the ground station, where the QND and quantum memory are situated here. And if you can do a quantum non-demolition measurements and know that the photon has arrived, and then you can store it, and then you know that this link is made, the there is an entangled pair is here. This entanglement link is made, and then you can carry out the repeater protocol. But this is very important to know that both photons are arrived and they're entangled. So that this is called heralding. It's a very important part of quantum repeaters. So we have to know that, and that's where the quantum non-demolition measurements come in. Now coming to quantum non-demolition measurement. Quantum non-demolition measurement of photon number by cross-phase modulation. So this is very similar to intensity-dependent refractive index change of Kerr nonlinear medium. So this proposal was a proposal ages ago in 1985 given by the Yamamoto group. And it is really based on the Kerr effect, where signal and probe are in different frequencies. This is what you can see here, that M1 and M2 are special mirrors. They are not regular mirrors. They are what you call dichroic mirrors, that they can transmit in certain frequencies while they reflect in other frequencies. So they are reflecting in the probe wave frequency, while they are transmitting in the signal wave frequency. So the probe is reflected from M1 and M2 mirrors, while the signal is transmitted. So what we see here is a signal goes to the Kerr medium, and due to the intensity of the signal, the refractive index of the Kerr medium changes. Because it's an optical Kerr medium, its refractive index changes depending on the intensity of light. And so its refractive index changes depending on the intensity of the signal, and then the probe wave goes, and because its refractive index has changed, it gives an extra phase shift to the probe wave, and that can be detected here using the detectors. So by detecting the probe wave, you know the intensity of the signal, or if you are considering signal to be a few photon signal, so you know if the signal was present or not, if you are considering a quantum signal. However, this protocol is only valid if both signal and probe are incident at the same time. So this protocol is not good if the signal is in a time being qubit, and it can be in 2 time beans, and you want to keep the time beans, and that's what we're going to describe next. If you want a time bean QND, where the signal is in a time bean state, not in a polarization qubit, but in a time bean qubit, the one I showed earlier, the early and late qubit. If the signal is in such a qubit state, what you want is that you want to store the probe in the medium, and then you send the signal. Then it does not matter that the probe and signal has to be coincident, and the time being state may not work well. So what you need instead of the Kerr medium is a quantum memory. And that's what was done more recently in 2016 in a proof of principle experiment by the Wolfgang Tittel group, which was in Calgary, right beside they were also in Calgary, like his office was right beside Christoph's, Wolfgang's, and that we visited that lab many times, but later he shifted to Delft. So anyway, so that experiment was the origin of my project, really. So that experiment was using a few photon signal pulse, and not a single photon signal, but a few photon, not few photon, a lot of photon signal pulse, but it's still kind of, it's not, it was still, the experiment was done clearly keeping in mind that we want to go to a single photon level signal, but they didn't reach there. But that was considered the designing the experiment. So the probe was stored in a memory. So this is a certain type of quantum memory called atomic frequency quantum memory. But anyway, let's just consider this as just a type of memory where the probe is stored, and then the signal is passed. this is in frequency space. So probe and signal have different frequency, and the signal gives the phase shift to the probe. It is very similar to the optical Kerr effect, how the phase, how the signal gives the phase, but it is to say it more specifically, it is the AC stark shift, the way the phase gets into the probe, and then you can measure the probe and know if the signal was there or not. However, this had a problem, an intrinsic problem, that the probe was in a coherent state, right? So the probe is a big pulse, it's in a coherent state, and this is the optical phase space, and it gets shifted due to the phase shift from the signal. And if the signal is a big pulse also with a lot of photons, and then it gets shifted comfortably, and you can distinguish between the case where there is no signal and the presence of signal. So absence of signal and presence of signal, you can distinguish them. But however, if the signal is too small, if signal is at the single photon level, these two overlap, and so you cannot distinguish them anymore. And this came out to be a fundamental problem, that you cannot, even in theory, send a single photon level signal and distinguish the two probe states in presence or absence of signal. If you try to give a higher phase shift by taking the signal closer to the probe, if you take them closer in frequency, you have a higher phase shift, but then the signal tends to get lost because they get absorbed into the memory, and then that causes a lot of problems. So this turns out to be a fundamental problem, and that's how my project originated, that the single photon level signal cannot be directly done by this scheme. So what would be the solution? So this was the background for my project. Now really my project is starting. So the solution was using a cavity. A cavity, an optical cavity, amplifies the electric field, resulting in a higher atom-photon coupling. So this was really this memory and everything. This was in rare earth ion embedded quantum memory. So it's like rare earth ion embedded crystal. So neodymium YVO crystal, or thulium in YSO crystal, things like that. And so this is just ion embedded in crystals. However, that itself, just doing it in free space, didn't work so well. So what we need to do is using a cavity, and this is like a photonic crystal cavity, which is a specially designed cavity, a nano cavity, where we can store the probe field and then send the signal. These time beam qubits, which can be the photon can be in either the early or late beam, or it can be in both beams, like it can be a superposition like it is seen here, and that won't matter. It will go inside the cavity and get reflected from the other end, because it's a one-sided cavity, and then come back out. That is the E in and E out, and it will give the both beams will give phase shift to the stored probe field. So we won't know whether the photon was in this bin or that bin, and so the superposition will remain intact. So the qubit state won't be disturbed, the photon won't be destroyed, and we would know whether the photon was there or not by retrieving this probe pulse and measuring its phase, just like the initial Yamamoto experiment of 1985. It's just a bit of sophisticated setup. The principle is kind of the same. However, the cavity gives a lot of issues. Cavity makes a lot of issues to this problem in the modeling. And what happens is that instead of the initial, this very easy phase shift, which is just a shift from here to there in optical phase shift, on the optical phase space, just the shift of the probe state. What happens due to the cavity is that this is the phase space now, and this is the phase space that is shown, and this is the probe state in absence of the signal, which is just a regular nice coherent state. But if the signal is present, what happens is that the state gets scattered all over the place, and it's no more a simple shift. However, our goal is not having a simple shifted coherent state. our goal is to distinguish between this state and that state in absence and in presence of signal. If we can distinguish, we can still perform the QND. So given that that is our goal, to even theoretically distinguish between the states, what we need is we need to know the inner products between the two. If the inner product goes to 0 and in certain parameter regime, then we can definitely distinguish in that regime. At least theoretically, we can distinguish, and that's what we try to plot here: the inner product with a certain parameter, and we do see in a certain parameter regime it does go to 0. And so here, at least theoretically, we can distinguish. But how to do it practically? In practically, we can do a quadrature detection scheme, which is basically saying that we want to measure the projection along this direction. And if you do that, we will find it at one place, and this will be scattered all over the place, like here. This is in absence of the signal, the probe will be here. In presence, it will be scattered all over the place. But they look quite different, and we can say if it is, say, less than 1 or something, if the value of the quadrature is less than 1, we say it is the signal was present. If it is more than 1, we say we don't know. So there will be some lack of efficiency, but we can say it very confidently. When it is less than 1, we can say very confidently that the signal was there. So the fidelity can still be high in the QND detection if we sacrifice in efficiency. So that's what I'm saying. That's is the conclusion out of these, is that quantum non-demolition measurement can still be done using even for this this scattered funny phase shift. We can still do the quantum non-demolition measurement using this quadrature measurement. And with that, I end the first project. And here the implementation needs a nano cavity. Many such systems are getting developed recently, and they are getting developed in different things, not just in rare earth ions, in like fiber-based things and other things. But to implement our proposal, we need a high cavity finesse in a long cavity, which is still not done yet, but it's people are definitely making good progress in that direction. So this may happen soon. Now coming to the next project, which is about Rydberg excitons. This is about exciton states in solids. Rydberg states in solids, and it was seen recently in 2014 in Cu2 excitons. So the Q plus oxide excitons. This is where the excitons was first seen in 1950s. We all know that we see excitons in semiconductors. But this is why it was first seen, and then now in 2014 it was the Rydberg states were also first seen in this kind of the Cu2 excitons. And the excitons are bound electron hole pairs in solids. So this is like an atom, like an electron going around a hole. And what is a Rydberg system? A Rydberg system are hydrogen-like systems excited to high principal quantum number, like Rydberg atoms, rubidium and cesium, where the outermost electron goes to a very high quantum number, like n equal to 100. Generally, it is at n equal to 6, but you can excite it to n equal to 100, and then at such high n, it has a very large radius. So normal atomic radius in like angstrom or nanometer, but this goes to like a micrometer, like 1,000 times more radius. So it has a huge dipole and a large interaction energy. Between two such Rydberg atoms, there will be a huge interaction. And this is what we can use. We can manipulate the atoms and take them to Rydberg state, and then we can use that huge interaction, because this interaction is also switchable. We can take them from n equal to 6 to n equal to 100, and we have the interaction, we can switch off the interaction. So this is a very useful thing, and hence Rydberg atoms, which is the main Rydberg systems like the rubidium and cesium. These were very useful in quantum information for both quantum simulation and quantum computation, where there's like quantum simulations were done using Rydberg atoms, which are done like 50 trapped atoms. Simulator was made in 2017 itself. Now there is probably like 250 a atom simulator with the Looking group in Harvard. So what we try to do is we try to do a similar thing here for exciton and see that if a quantum simulator for exciton can work. But before we go to that, let's revise the main properties of the Rydberg atoms. One of these main features is a Rydberg blockade, where if you excite one of the Rydberg atoms within a certain radius, you cannot excite another atom. Why does that happen? Is that if you excite one atom, it's excited. What happens is that other atoms' excited state gets shifted because you can think of it as like a Stark effect. So this atom is excited, and there is a form of a dipole, and this dipole have an electric field, and that electric field is shifting that excited state due to Stark effect. It's a simple way of thinking about it. The interaction is much more complicated, really, but it's a simple way of thinking about it, that it's shifted. And that shift goes to n to the power 11. So if n is 100, so this is like 10 to the power 22. It's a huge shift. But then this is like r to the power 6. So I mean, if you try to excite the other atom using the same laser, it gets blocked. So within a certain radius, because it's r to the power 6, within a certain radius, this is you cannot excite any other Rydberg atom if we excite one of the Rydberg atoms, or any Rydberg system. For any Rydberg system, if you excite one, that you cannot excite another within a certain radius. That is called the blockade radius. Now, this is the Rydberg exciton experimental graph, which is showing the spectroscopy of Rydberg excitons. And you can see the exciton states. This is n equal to 2. It starts with n equal to 2, n equal to 3, and then these states are crammed together. But you can zoom in and see they have gone to states to n equal to 22, which are like very close together here. So this n equal to 22, 23, 24, up to n equal to 25. They have seen states, and these states are huge. They are like 1 micrometer in extension. So they are like Rydberg states. And using this, we try to propose. We proposed a quantum simulation experiment using this Rydberg excitons. So what we proposed here is that the simulation of quantum many-body dynamics. So this is we have a polygon, n-gon, and on each vertices of that n-gon, we are shining a laser to create an exciton. And when an exciton is created here, then this exciton would have a Rydberg blockade radius, RB, and that blockade radius is greater than the side of the polygon, the side length of the polygon, and hence two of the nearing excitons cannot be excited together. So both cannot be in the Rydberg state R, which is defined by the R. The two neighboring sides cannot be both excited to the R state due to the Rydberg blockade. So if we shine the laser at every spot and everything goes ideally, then what kind of state would we have? That is what we want to find, and that is called objective state. Now, this is a very simple example, so we can understand what kind of state we'll have. We'll have a state like that, either GR, that kind of state, or RG, that kind of state. Where G is like a ground state where there's no exciton, and that's R is the state where there's exciton in the Rydberg state. So there cannot be two neighboring state excitons in R state, that we understand. And if the lasers go well and it is exciting excitons properly, then there cannot be two excitons in G state either, right? If there is one in G state, the next one will be excited because the lasers are there, they are trying to excite the excitons to the excited state, so they will be excited. This is an 8-side polygon configuration, and we did the simulation from different number of sides. And finally, this is the result for the maximum site we saw. It was for 12 sites. This is the probability of top 7 states for 12-site polygon. And we see that the objective states that we show here are the maximum, have the maximum probability. This RG, and GR state, they have the maximum probability, or the highest probability. There are some probability for other states though, and that is because we have done a complicated simulation where we have modeled the whole system, not just including the Rydberg state, but also neighboring states. So this is say n equal to 23 is say the Rydberg state, and then we are also including n equal to 22 and n equal to 24 there, because we want to know the effect of the laser on there, and that because you can see these are not like very clean states. There is a lot of noise and other things. So that's why there is this. We see these other states that comes in the effect of that. And they are very close together. The states, the effect of which can be seen here. If there is just one state, we will probably just find these states in the objective state that we want to find. So the other signature of the Rydberg state is that we would see this correlation function, which is like this is like the exciton sites 2, 4, 6, 8, 10. There is like 9 and 7 in between, so this is all sites there. And this is also the sites, and we see the exciton correlation. The middle ones are just self correlation, so they are of course highly positive. But the next one is the correlation with the nearest neighbor. So that is negative. So if this is G, that is R, or if this is R, that is G, things like that. So this is a negative correlation. But the next nearest neighbor is again positive. And it goes on like that. After a bit, the correlation decays because there is just not enough, not enough correlation over long distance due to all the errors that accumulates. So the same graphs were seen for the Rydberg atoms when the simulation was done for Rydberg atoms. So this is confirming the Rydberg exciton dynamics. And we have also done an application of this maximum, what is the maximum independent set problem. So there is a graph like this, arbitrary graph of points, and the points are connected to each other if the distance between them is less than 1. So then there is a connection. So the 1 and 8 say are not connected. Neither is 1 and 7 because the distance between them is greater than 1. So the unity radius circle around 1 is shown by this. So these are all the circles around each point, and the ones that are within the unity radius of 1, unity radius circle, they are connected to 1. So 2 and 3 are connected to 1. So what we want to know here is that what is the maximum independent set of vertices, maximum number of independent set of vertices that we can find that won't be connected to anything. So like say 1 and 5 and 8 and something like that. Like if we take 1 and 5 and 8, these are not connected to each other. So this will be an independent set of vertices, but this may not be maximum. This is just 3. Maybe there is 5. Maybe there is 7. 7 number of vertices that we can find that won't be connected to each other. So we want to know the maximum number and possibly the solution too. Like what is it? Is it 1, 5, 2, 8 or 1, 5, 7, 9 or what is it? What is the maximum number of vertices and what would be the configuration corresponding to that? And this can be done by doing that simulation. You shine the laser at each point, like we did for the polygon here. We shine the laser at each point, and then we let the Rydberg dynamics happen, Rydberg exciton dynamics. And if these two are connected, so what we have to make sure is that the blockade radius is the same as that distance, the unity distance. So if these two are connected, they are within the blockade radius, then they cannot be excited together. So we won't have two excitons within the blockade radius, and hence we would naturally won't have like connected ones. Like those would be like a dependent set where these two are connected. So we would have an independent set, and that experiment was done here, and we would see here that the two high states are both 5 excitons, like this one. Which one is this one and that one, the purple and the brown, purple and the brown. Yes, these two both has like 5 excitons, and that is the highest probability state. again, due to the other states and all that, there is a lot of errors there. But we do see the highest number of excitons here using this application. So this is these are the simulations that were done in like classical computers with very limited capacity, and we still see the effects. So that was my talk, kind of. And then there is one further result is that we saw a highly efficient indirect detection scheme using this Rydberg excitons. That kind of came as a byproduct of this protocol. We devised this very efficient indirect detection scheme of the excitons, where we can detect the excitons with high fidelity using like an atomic gas microscope kind of. That was the Rydberg atom analog of that, of such a detection scheme. Like the atomic gas microscope, you can really see the excitons, the Rydberg atoms very well, which atoms are in the Rydberg state and which is not. And the similar thing can be done here. So that was it. Thank you. Any questions are welcome.
Okay,
yes,
so if you have any questions, yeah, you can unmute yourself and ask, or you can ask through the chat box.
No, I'll unmute and ask directly.
Yeah, please go ahead.
This is the early and late photon states. And what is the typical time domain difference between these two?
So the early and late photons, they are generally, it depends on the, it can be really anything, depending on the other parameters of the experiment. But here, the experiment that was done here, as far as I remember, this one, for this experiment, this one for that signal was, I think, in the signal was around like 3 meters, so like 10 nanosecond signal. So it was in that regime.
So the signal was 10 nanoseconds. So you think it's about 50 nanoseconds or something difference?
Something in that region. Yeah,
you're saying signal width is 10 nanosecond.
Yes.
What's the difference between the early pulse and the late pulse?
Yeah, it was made sure that there is almost vanishing overlap between them.
It's almost vanishing overlap. Okay.
Yeah, so there's like orthogonal. Yes.
Okay, and that in teleportation, you said that this entangled photons, that's A, B, C, D, you have shown. What's the typical distance of those?
Yeah, so this is individual links of quantum repeaters. So this is, we want this link so that this links get successful most of the times. So right now, the repeater protocol, these links are really small. I mean, in the lab, it's like a few meters. And then if we go, I mean, in the starting experiments, then we went on. And right now, there are some links that are happening over the metropolitan cities. Like there was one experiment where there was a link between the Calgary University and the Calgary City Hall, which is like 10-15 kilometers. So that is kind of the link we are thinking about now. But later on, when this memories become better, so the link distance depends on the memory.
Is that link also through optical fiber?
Yeah, that link is through optical fibers. This is like a fiber-based repeater.
Okay.
Sorry. I'll just get
some water. Another thing is that the car method that you showed.
Yes. Sorry, I just got some water. Yes.
The option with the car signal.
Yes.
So your signal wave and the probe wave, they are different in frequencies. What's the typical frequency shift there you need?
So this will again depend on the medium. So with like the car medium, it gets a phase shift in certain frequencies, because this is like really the refractive index change, right? So refractive index is frequency dependent. Medium.
That's what I'm saying. If you change by a few hertz, it will not change much. That's why. What's the typical frequency difference between these two?
Right. So this will depends on the system, I guess. But here in this experiment, you can see this was really in arbitrary units, but this is here. It is actually resonance. The probe is in resonance with the atoms, and then this is the signal. So this is more like in gigahertz. The things that I have estimated for our experiment, it was in gigahertz.
Okay.
So here it is more like an AC stark shift, where the signal is giving the phase shift to the atoms, and it is in we have AC stark shift, and the phase shift in the atoms really goes as a phase shift within the probe, which are later retrieved and measured.
But these atoms, what atoms are these?
These are rare earth ion quantum memory. So this can be, these are really the rare earth ions in the periodic table. So this can be thulium or neodymium.
Are these isolated ions or within some medium?
It's within a medium. So it's like a YSO crystal or YVO crystal, yttrium orthosilicate or yttrium vanadium oxide, those kind of crystal. So these are not so hard crystal, but these are like crystals in which you can embed the ions either by ion beam thing, or just putting them inside the oven with those ions and things like that. You can embed them, the ions, within the crystal, and then that ion is like it's like ions in vacuum, ion trap thing, but instead of vacuum you have the crystal, and then the crystal holds it, so you can just have it in your hand and take it from one place to another instead of doing the complicated trapping for ions or atoms. But then it has its problems.
Now the question is, your x-axis is frequency or time.
Right.
Now, what is the typical separation between these peaks, spatially?
Spatially,
the peaks that we are saying, they are supposedly spatially shifted positions, right?
No, this is in frequency. This is in frequency.
That means now physically, how we are putting these things in?
Physically,
if it is in a single crystal, you have different frequencies.
Yes, so this is like we are putting them in by the probe is put within the memory in the crystal. The ions are embedded, and the probe is stored within the memory, where the signal is just it is detuned. It's off resonant, and it just goes over. And while being detuned, it gives some phase shift by the AC stark shift. So it is not absorbed. The signal is not absorbed. So it's just it just moves to the crystal and gives some phase shift, which is later seen.
Okay, sure.
Okay, so any other questions?
I have some questions.
Yes, please. Yeah.
If I have some time later, I'll ask some more questions.
Yes, please. Yeah. Okay.
Okay, so I'm Aditi here. So I actually, first thing I want to say that when you say about the repeater, so the original repeater problem actually also involves the distillation, because all these states that you will create in experiments, they will never be the exactly maximally entangled state. Right. So over the distance, you cannot really create maximally entangled because they will be noisy, right? And right. So you have to either you do it with a noisy thing, and then you want to see how your, what is the critical noise that you allow, or you actually have a distillation protocol. So I think the experiment that you were talking there, of course, as far as I know, there is no distillation experiment as such, where the quantum repeater, truly quantum repeater problem, which was proposed by Hans Briegel and et al., this was done, right?
Right. Yeah, this is like, these are like first generation repeater where we are just trying to store and have some entanglement and things like that. Like those, yeah, Christoph says those are like second generation repeater where you try to do
I'm in the
error
office. I
correction and
just
all
have
this.
to see someone for a few minutes, 2 or 3 minutes, and come back. Yeah,
okay.
Can you just take over for a few minutes?
Yeah, sure.
And then when I okay, or maybe you can conclude it, and then we can move on to sorry.
Okay, are you telling me, Professor Dutt?
Yeah. Okay, so I just have this someone who's come from outside. I just have to see the guy.
Oh, yeah, sure. I have some questions, so we can continue.
Okay, thank you. Thanks.
Okay, so I mean, I just want to understand the Calgary experiment that you were talking. That's just only the performing measurement or doing teleportation, right?
The repeater experiment I was talking about.
Yeah. You said that in Calgary there is some from the college, university to the city. There is some experiment.
Yeah. Yes. Yeah, that was more about, this is not even a complete link of a repeater. It's like a half a link of a repeater. It was more like a teleportation experiment.
Exactly. So now whatever you are presenting, it's more like an entanglement swapping experiment, right? I mean, rather than we should tell the repeater problem, because there we don't know about how the noise ratio will scale, because it can happen that depending on the link, actually finally you only get noisy states which are no more any useful, right? It can happen.
Maybe. I think I mean the people in Delft, the Ronald Hansen and people, they have done something like that is very close to the repeater with single NV centers. But yeah, this is still
then the distance is compromised.
Right, then the distance is compromised, right? Exactly. Absolutely. Yes.
And also, I think, as far as I know, there are many proposals of repeater and in network. Even in our group at HRI, we have some proposals. But everything now people are trying to see that how we can really get rid of distillation protocol and can do the repeater. Now, my second question is about this, exactly the figure that you were showing. So here, this time being signal that you are kind of putting into the probe, okay? So this also in your calculations, you assume they are all kind of in a pure state, or you also consider noise in your calculation?
What kind of noise?
Because this has some time bin or whatever you are creating, that has with certain fidelity you can only get, right?
No, we don't consider that noise. We consider other kind of noise. Like we don't consider noise in creating the state. Like we think like, yeah, we have assumed that we get a like complete pure single photon state, which is in a time bin state. Like you can create time bin very easily. You just use what is it, the interferometer with 2 different path lengths, and then you have a time bin.
But that also, I mean, now the fidelity is very high, like 99.5, but it's of course not 100%. There should be some noise, right? Okay, but you assume that it is noiseless. So it's a perfect pure state that you send it to probe. So what kind of noise you actually introduce?
So the noise is more like this state would, if this state gets too close to the atoms, the signal, then this will be absorbed. So that is a loss kind of. So that has an effect. Then there can be, if the probe is stored, there can be like stimulated emission. That is another kind of loss or noise that you can say that's a noise. So these things are considered, but we have not considered the effect that the signal itself is distorted. It can be there, but because the signal is just going and getting reflected and coming back, I'm not sure if that is a big issue for us. I mean, it can be, and we have not thought about it in detail, but it's like the signal is not really affected. It's just going, getting reflected from the back mirror and coming back.
Okay. But there should be also some impurity in your crystal, right? That will affect the output signal, right?
Well, if the impurity is in resonance with the signal, then yes. But if it is the impurity is in like a very different frequency, then it should not be. If the signal especially is in a small frequency range, and then the probe is in a, I mean, the probe is in another frequency range, and the atoms in that frequency range, things like that.
Okay. Okay. Yeah. But so you actually the output state that you consider, and then you probably show in the next slide something like kind of inner product, like a fidelity, right? Is it?
Yeah, this is the inner product between the not between the signal, between the probe states, between this state and that state.
Okay. So this is just a fidelity calculations that you do, right? This is inner product means fidelity.
No, well, it's no. This is to distinguish between this state and that state.
Yeah, so, yeah. So the inner product square is fidelity, right?
Yes,
that is called fidelity.
That is for the signal, but this is for the probe, really.
But so whatever, anything rho or whatever, in your case pure, so it's just an inner product between psi and phi modular square always gives you fidelity, that how close you are with the probe, right?
Right. So here we say we are not close at all, it is 0. So we can distinguish.
Okay. So when it is 0, actually that's better. In some sense, then you conclude they are orthogonal, and so that you can distinguish, right?
Exactly. That's what we are trying to do.
Yeah, but even when you have I see that you have usually when even it is not 0, then you know that they can be non-orthogonal, but still you can distinguish with certain probability. But that you haven't considered. Oh no, that you consider in the next, or is it?
No, this is in that regime where the inner product is almost 0. But when you try to do it practically, to find out the exact distinction is very difficult. So we put a practical method where although the inner product is 0, you still cannot do it perfectly, but you can do a pretty good job. That's what we are saying. By doing quadrature measurement.
So in some sense, you assume that both the output and the probe, whatever this thing, they are all in pure states, right?
Right.
Okay, but will it be the case really in the experiment?
Well, they have done the experiment for the thing that we are proposing here is for single photon signal. There is no experiment on that, but they have done the experiment for sorry, for large signals, and that they did not have much issue with the signal or probe impurity, but then these were large signals, so this may be different.
Okay, so maybe we have time for just one more question.
If nobody else is asking, can I ask one question?
Or shall we wait for anyone else to ask, just in case?
Okay.
Any other question? Okay, if not, yes, please. Okay, yes, go ahead. Yeah.
Okay, so this is the last question that that you compared this Rydberg states for copper oxide case, solid state. But for atoms, I understand that each atom is in Rydberg state or the ground state.
Right.
And they are separated when you create a lattice of that. But in your case, it's the copper oxide. Yes. I understand that your exciton radius is about 90 nanometer. That's what you mentioned, right?
The exciton radius, it's about a micrometer.
A micrometer. Okay,
yeah.
So
here
you can actually place your copper oxide unit at that separation. So what's the smallest size of your copper oxide? So you have dealt with the 12 side cases.
Right.
So each side you have to have copper oxide. So what is the physical size of that piece of copper oxide?
No, this is like this is a whole copper oxide crystal. So the whole crystal is of copper oxide, and these two dimensions can be large. The thickness has to be small. It has to be like 3-4 micrometer within that. Whereas around 4 micrometer is a perfect one. That's what we are calculating in our paper. And if you shine the laser at one spot, it will create only one exciton because of the blockade radius and the size of the exciton and everything. In general, it can create many excitons if there is no blockade effect. If you are creating n equal to 2 excitons, then if you have a large enough spot size of the laser, you can create many excitons. But here, because
now my question is that outside this radius,
yes,
you don't have only these 12 points. You have many other points.
Right.
So you can get excitons from there.
Right, but the laser is not there. Laser is only here. It's very focused laser using a micro lens. You focus it on this point. That is our proposal. The laser, all the intensity is at that point, and then you can curate the intensity and the focusing such that then in the other points, the laser intensity is almost negligible, even with the spot, within the spot. And then outside is, of course, there is no laser to excite.
Okay, so at these 12 points, you can direct the laser so that it doesn't spread much, the laser spot.
Right.
Okay. Thank you.
Thank you.
So, okay, Sumit, thank you for a very interesting talk. Which led to a lot of interesting points being raised. So, thank you again.